Okay.
Thank you. Thank you.
Dr. Jalza, I don't know how you're going to manage the questions in the thing.
It will be typed in the Q&A window, sir.
Okay.
If questions comes, I will read out. No problem. At the end of the presentation.
Sounds good. Thanks a lot, Dr. Jalza. So let me go forward. Again, as I said, I'll just go over the application characteristics. Some of these things you probably know, being involved in it. I don't have a very clear idea about the entire audience, but assuming you being in the technology, you've been in the industry and the education field, you probably know a lot of these things already. But what I'm going to link with is how the infrastructure has evolved and how these things matter to each other. It's almost like a chicken and egg, which one influences what, like which one came first kind of a thing. Whether application impacted infrastructure design or infrastructure design enabled applications to go to a different level. It's very, we don't know which one is influencing what, but I'll go. But what I will not cover is application technology trends. I will keep it aside and we'll not talk about what does it mean to AI, ML, or blockchain, or those things. This is very, very fundamental because it will question some of the basic assumptions that we have, and also gives us some perspective on what are the design considerations we have to do while building either cloud infrastructure or building applications for cloud infrastructure, right, in the cloud system. Okay. Some of the topics I'll cover are application architectures, infrastructure architecture that I will weave into the whole talk, impact on each other. That also I will weave into all the slides. And then where we are in terms of both application architecture and infrastructure, and what are the things that are going on. What are people working on and then take away, and then we'll have a question and answer session in the end. I have around 25 slides to cover in a matter of maybe 40 minutes. So I'll probably go faster. Feel free to note a point or ask me a question at any point of the time, and then I'll slow down and answer your questions. Okay. So let's look at how applications have, or the architecture has evolved over the time, right? Obviously, when it started, they were all monolithic. They're all running on one computer. If you want more performance or anything, you just put more memory, more CPU. That's how the applications were built initially, because that's what architecture allowed. Whether you all the way start from IBM 360, 370, Von Neumann architecture, or any other early 70s, 80s, 1980s, 1970s architecture. That's what the applications are built on. One single monolithic application, right? Mainframes were there, and then mini frames came, and these applications ran on those things. And then came three-tier architecture. You have separated client, you have separated applications, you have separated databases, and then that allowed people to scale different things in different levels, so that it enables the solution to give into the user without having to spend too much on one single monolithic thing, because every layer had a different scaling requirements, or stability requirements, or availability requirements, and all that. Then coming all the way to 2000, late parts of 2000, the internet and all these things came, and we evolved into service-oriented architecture. So the applications have become not like a client or middle layer or a backend layer. It's basically, hey, I will do this service. You use me to whatever you want. Like I'm a database as a service, or payment as a service, or anything that full functional as a service. You don't care about whether that has a 3 layers or 1 layer or 2 layer. All we care about the service definition, and that gets integrated into application and do it. And with the advent of mobile and that infrastructure rapid explosion into the world, this became really, really popular, and applications have caught on to that. right? Again, I'm just repeating, you probably know all these things, but just gives the context about how these things influence the cloud infrastructure, right? Then off lately, right now, currently everybody is into microservice architecture. So everybody now builds, they all start with a microservice. That is, okay, what does this service does, and define the API, and you don't care where the system runs, and that carries its own state, so it can do on its own the scaling and availability requirements, and the consumer which is using the service doesn't have to bother about carrying everything. It's almost like in a monolithic world, you have libraries. These are microservices. The libraries have to be carried with the application, and application has to worry about whether it's running, how much CPU it is taking, how much memory it is taking. Whereas in the microservice architecture, you just the contract is the API, and the where it runs and how it runs. I mean, the consumer doesn't bother about it, right? So it gives the freedom to the developer to develop rapidly and not reinvent the wheel all the time. So these are the kind of thing. Off lately, I'll talk about in the later part of the thing. There are also the new paradigm, which is called serverless architecture, which is not entirely modifying everything to from microservice to serverless, but a certain kind of applications are being rewritten and designed in serverless. I'll talk about the advantage of that, all those things, and how the infrastructure is changing. Okay, so if you look at we just talked about how the applications have evolved from a different architecture to a different thing. Right now, if you take microservices, all the way from monolithic to microservices. But what are the factors? Understanding those factors will give an insight into how the infrastructure actually caught up with that, right? If you look at that, first and fundamental thing that actually impacted this architecture is the number of users that actually start using this service or the application has tremendously increased. I mean, I'll show you some numbers which are staggering numbers. Just because of the mobile and the internet, you write an application, put it in, suddenly then that application will be used by millions of people if you have a proper channel to reach out to them, right? And the internet allows you to reach out to these people. So now the old architectures you cannot handle this kind of thing. Either it is too much to download and run it, or there is a state that needs to be kept somewhere in the central so that everybody understand that. There's a collaboration requirement, and that means that it can't run locally. It has to run in the central place. And then this the user base growth impacted the application architecture tremendously, and how the infrastructure will go into that. The second factor is the application areas. We'll go into that as well. Right now, software eats everything. That's what people say. Software is in every place. The one that mops our floors has software in it, and the one that controls nuclear reactor has software in it. That I don't have to say, right? IoT has bringing a lot more devices into the network, a lot more computing controls into the entire software architecture, right? So that's another one that impacted how the applications have evolved. But the most important one is the scalability, reliability, and availability. These are the three parameters that impacted the current software architecture and cloud architecture, predominantly impacted by this particular requirement. That is, they require that the application has to scale, application has to be reliable and available. This itself is, and I'll stress a lot on this aspect of it to tell how much it impacted the cloud infrastructure. Then the performance, then security consideration, and last but not the least is the burden on the developer. That is, for a developer to build this kind of applications, which will address the user base growth, address all kinds of computing models, address the scalability and reliability, availability, performance, and security, and also worry about the business logic that he has to write, right? One developer or the team has to do this. It demands a lot of skill sets, because each individual pillar that we talked about itself is a humongous amount of theory went into it, and people have to know about these fundamentals and then expertise to write an application that addresses all these pillars. So the burden on the developer is also is an important factor to consider. while you're building the infrastructure. How much you can take away that particular complexity from the application so that the developer can focus on the business logic, what that service is supposed to do, rather than how it has been maintained, how it has been deployed, how it has been secured, how the performance is managed and availability is managed, right? So the mobility of the application is putting a lot of it. That is, application can run anywhere, and also the velocity of the development also. So we'll go through these factors one by one. I will not specifically go one by one, but I will weave into these things to tell how these factors impacted the cloud infrastructure designs and concepts, and how it is evolving over the time, right? So if you look at the first factor, that user growth, this is already a 1-year-old data. The latest data is still not published.
Excuse me,
Yes.
sir. Your slide is not. This is the first screen. It's like that.
Is it same for everybody? I can see the 6th slide.
Yes. Yeah, you have to double click on that. The side, you have to double click on, then only it will be visible for everyone.
No, I can see the slide moving. Is it same for everybody or you only?
No, for everybody it is same, sir. This is the first slide.
The slide movement is not there, sir.
See, I'm using the file that I uploaded, and
Okay.
I'm on the 6th slide currently. That's what I'm seeing.
Sir, that is.
But we are not.
Sir, that you have to double click on the side window. Some slides, the slides will show now. There you have to double click. Then only it will be visible for everyone.
I'm not sure.
The previous slides will be there at the side, right? There you have to double click.
If I'm moving, I've seen the slides 2, slide 3, slide 4. You guys are not seeing it?
No, sir.
Okay. Share the content. I shared the file. Now?
Now also, sir. Sir, in the PPT presentation, your the PDF format or the PPT format?
It's a PPT format.
Then in the slides, in the side, it shows the number of slides at a time. So there you have to double click, not in the single slide. The slide we used to get no slides as well as outline. There you have to double click.
Where do I'm viewing IEEE 1st August.
Yes. In your screen, there will be a PPT presentation.
Can you?
Number of slides, sir.
Yes, madam.
Yeah. Double click on that.
I double clicked on that. I mean, can you access my slides?
No, you have to share with, then only I can access.
I shared using my thing, right?
No, I can't move. The entire PPT, if you are shared it, I can.
I shared entire PPT, yes.
No, sir. You have to share me with my email ID or through WhatsApp. Then only I can use it. Otherwise,
Okay, let me, I don't know. You want to give me your email and I'll send you my slides?
okay. I just type here.
Sorry about that. I don't know. I mean, I used WebEx, but I didn't know it was this complicated.
No, sir. No, I think you have to double click on that. That's it, right?
I've been double clicking, triple clicking, so I don't know what.
Okay, sir. Okay.
I sent you the slides.
Oh, okay.
Oh, okay. Did you get my slides, please?
1 second.
Yeah.
By that time, you can share your views, sir, so that I'll share. Take all of the and talk to the person. By that time, I'll share the
Okay. Fine. So let me move slightly ahead. I'm on the slide 6. Dr. Jalja, if you can upload your thing and
sure.
navigate. What this slide tells about is number of users right now we have on the internet, according to last year's statistics, which is basically we have almost 5 billion users on the internet, which basically using software and services that are provided either through mobile apps and backend services and all that. So you can imagine you develop an application, you have to think that service going to be used by, if not for 5 billion people, 0.001% of it is going to be a pretty big number. So the scale at which this users growth is going is humongous. So it can no longer build applications if it has to be given to the. So just let me know, Dr. Jalda, when you can upload. So.
Yes, sir. Sure, sir. It is downloading.
Okay.
Yeah, you can see.
Yeah. So that's the user growth that is impacting the application. So you need to now imagine any application that you have so far developed. Imagine that application is being used simultaneously by 10 times the current user. So if you're done, say, suppose you're done something for your school or your college, for your educational institution or your small industry that you're working on, and if there are 10 users, imagine if there are 100 users using the same time. Will that application work, right? Will that, do whatever it's supposed to do? Does the CPU is enough? It has been enough or not? Is the storage enough? Do I need to plan this in advance? Which basically means that it's not designed for it when the service has gone live, right? So these are the considerations that the user growth is putting a lot on the application infrastructure or application architecture. So what it means to the application architecture means that you say first split your architecture into two. One is whatever I do for the interface, whatever I do to the number of users, I will compute that separately, and whatever I need to do to business logic or backend services, whether I have to do algorithms, I have to do a lot of I/O, a lot of everything, I will separate out. So the two-tier architecture has come into picture. So which basically means that I need a different architecture than an existing one single mainframe kind of a server that need to that. So that again led to the next as a client server architecture. And then what happened is that now you have a humongous servers, which are very powerful one, but has a different requirements of heating, AC, management, all that. Yes. Okay. All that, and then you suddenly see a data center coming into picture. So which is what happened in late 90s or early 90s actually. The data centers evolved where all these servers that are actually doing the computation, which requires humongous CPU, memory, storage, and network, have gone into under the four walls that nobody enters. It has a different heating requirements and ACs. And then people connect to that using PCs and their mobile device and all that, and do that. So that's the first architectural change in terms of how you manage your art, which is basically the number of users growth is forced the split of application into two layers, and one layer went into the data centers and the dark data centers, and other one sit into your PCs, and maybe later the mobile device, right? Okay. You still getting the slides, Dr. Kalja?
Still it is down.
Okay. Sorry about that. I don't know where to double click here. It's pretty.
It's okay, you can proceed.
Okay. So, then that's one aspect of it. That is, your computation has moved into the data centers. The second aspect of this user growth impacted also where the content is going to be delivered. That is, so if imagine yours is a website, or you are serving some content, whether it's a video, images, HTML pages, or anything. Now, definitely you putting in a data center is not going to help because your user base is all over the world, right? So because we are talking about the global, that's great. So I'll just wait for a second while Dr. Jalda is sharing her slides. Okay. So, while the compute, memory, all that moved into the data center, the content, which is basically storage, cannot be moved there because then it won't serve you in a fashion in which that needs to be served, which is basically the speed at which it is to be done, right? So then the next evolution happened in that aspect is called CDNs, the content delivery networks. So the application now got split into two, but the second one got split into two again, which is basically a storage or a content delivery. Whenever the content needs to be delivered, it goes into content delivery network, and that content is basically spread into the world, into the web of network that the content delivery network guys have created. So one of the companies that you probably might have heard is Akamai, which is still the number one in that space of serving that. But what it gave basically the application is that, okay, if you have a content that needs to be delivered to the users who are in all over the place, you certainly cannot be delivered from one central place. It has to be distributed. So suddenly that your logic has to push the content to these edges. And so the infrastructure suddenly has evolved into, while the compute has moved into a central place in the data center, the storage has come in. Obviously, not all applications require this, but most of the content delivery, the content like websites, video servings, or those kind of things, started getting into that aspect of going into the CDN network. So the application architecture now impacted how the infrastructure has been built. So all these guys who supply content delivery network for service for you as an application provider have created these POPs and everywhere in the world where they have, like Bangalore has 4 POPs, for example. Delhi has few POPs, which they call point of distribution pods. And then there is a software which will distribute the content here. So as an application, will say, hey, go on to the 8th slide for me, Dr. Giles. You stopped sharing, I guess. Did we lose? I think we lost it. I'm sorry, guys, with this mess up. I don't know how to share this. Can you guys see my slide? Anybody? Hello? Can anybody hear me at least? So you guys can see my slides? I'm going to probably ask. Yeah, sounds good. So the CDN infrastructure, as you can see, is one of the architecture that came into play a role in the network. Okay, so this is the new thing that came into infrastructure apart from the data center. So the compute moved into data center, and the storage network has moved out of the data center to enable it. So you still have two layers. Application is still a client side and the backend, but backend has tentacles onto the CDN infrastructure. So that's the next one, right? Now, I hope you can see the slide 9. So now we talked about the user growth. Again, this itself is each topic is a big topic on its own. I can go into a lot more details, but I'm only covering at a high level these things, so we can go into details later if you have any questions. So we talked about the user growth, how it impacted the application architecture and the infrastructure architecture itself. Now coming to the areas in which the application runs. Now you have compute-intensive applications, you have streaming applications, which are mostly network intensive. Then you have communication applications, which are again network intensive, but a lot of stringent requirement on latencies and all that, right? So in the compute-intensive applications, you have examples like data analytics and modeling, simulations, ML, AI training model, a lot of those things. So suddenly these also started impacting what kind of infrastructure that you need to build to serve this kind of thing, and how the applications evolve for that, right? So now we are at a position from where a monolithic, a single server, we have come to the data center, and the data center has tentacles into CDN network kind of thing. But within the data center, what are the things that happen, the infrastructure, and how the data center architecture has changed? It is not just one single rack or one bunch of racks, which is a huge CPU, which connected to the net, and you could adjust through the client and do it. It has a structure to it, because that required a lot more things. So if you go to the inside, if you look into the inside thing, that's when the lot of hypervisor technologies also came into picture. So you have the data center, you have a router and a firewall at the edge. Then you have a layer 2 switch. Then you have a management server that manages all the infrastructure. Then you have a common storage, which is a primary storage for these nodes. And then you have a secondary storage, which is cheaper and slower, but it is for storing these things. And from the secondary storage, you have connectivity to the CDN outside. Whether you directly ship it or you ship it through secondary storage to the CDN network is decided by how your application is managed. So the guy who is developing the application, he or she, is worried about only, hey, do I have enough capacity to write the content, and you have enough capacity to compute whatever I need to do, all that, and then people manage this compute in there. So this is a simple data center. This is how the data center looked like at that point of time, right? Now, if you look at the next level of data center, now is to scale the data center. Now, how do I scale that? Which is we design thing into a pods. That is, I have a point of distribution within the data center, which will have its own storage, its own compute, and its own network. So they're called top of the rack switches. You have a management console that manages all these things. You have on the top, you have a layer 3 switches and firewalls and connected to internet. So what this enabled application is to not worry about whether I have the capacity to run this or not. If I have to scale, if I have to install multiple applications of the same instance, do I have enough capacity, or does the other application performance bother matter to the application that I am concerned about? So it's basically an isolation to a certain extent, and also make it independent of the hardware. So that if I have a problem in the storage, I take it out and put in a new storage, and the application doesn't need to know. Like for example, if you go into monolithic applications install on a particular dedicated server, if something goes wrong in that particular server, no, you have a problem because the application comes down, and the application has to be aware that, hey, the hardware went down and all that. Here, application assumes everything is failing, but when it fails, you have a secondary thing which is helping you out, and then the interface will remain same. Nothing changes in the network side, and you go forward. So now the data centers have evolved into a much more defined architecture, which is basically they have their own modules, a point of distribution, which are replications, and they also sometimes referred as unit of scale. That is, when they want to increase the capacity of the data center, they will add these new pods into the system so that more applications can be installed, right? So your application architecture has evolved into two layers. One is the client and the backend. And the backend is for capacity management. Now you've got a new logical structures in the data center so that the application developer doesn't have to worry about those things, right? So that's the the second aspect of it. That is where it is running. Whether compute intensive or various aspects of it, you have localized silos within the data center that enables you to deploy those applications. And the most important aspect that impacted the infrastructure behind of the requirements of the application is scalability, reliability, and availability. Again, we go back saying that when you develop an application nowadays, because of the internet and mobile and connectivity and everywhere, you put a service out there. This is humongous request that you'll get. So you need to be designed from the ground up, from the day one, to be able to handle this much of load, whether it is compute load, request load, storage load, IO load, right? Just to give you an example, what we're talking about, Google searches, that is, they receive almost 70K searches per second today, right? So 70,000 requests per second they get, which obviously they have different data centers all over the place. They're serving all these things, but that's what they have to manage. So if they launch a service tomorrow, like for example, they're launching a Gmail tomorrow, that application has to handle minimum of 70K per second. Otherwise, you consider that as a slow and you won't do it. Similarly, if you look at that, right, 5.7, that almost 6 billion searches per day they do. So imagine we have to write an application for that. And if you have to write an application developer has to worry about what kind of CPUs I need, what kind of infrastructure I need, what kind of network I need, all these things, or CDN I require, then they won't be ever able to write how to do the search actually, right? What algorithms I need to do, what kind of HLL algorithms I have to do to efficient search, what kind of indexing I have to do. Instead of worrying about that, you'll have to worry about the infrastructure. Similarly, the availability requirements. If you look at Microsoft, if you look at all the top-level service provider network services that provider you have in the world, most of them, if not 5 nines, they guarantee 4 nines. When I say 4 nines, which is basically 99.99% availability. 5 nines means 99.999% availability, which basically means that if you convert that into actual time, their downtime is guaranteed to be no more than 5.26 minutes per year. That is less than a second per day. That is, your availability of the service has to be less than, non-availability should be less than 1 second per day. That's how you have to design the application. So how do you design the application, and how do you worry about infrastructure that gives you these guarantees? And the difference you will see is if it is 3.9, that is 99.9%, which is not a joke either. That's also very difficult to achieve. If it is 99.9% availability, it is 8+ hours per year. I forgot to put per year there. So it's 8+ hours per year. So you can look at this, right? Just because it's 99.999, it's 5.26. The moment you get to 99.9, it is 8+ hours. That is the difference of availability. And to get to the magic number of 6 minutes per year downtime maximum, you have to have a application architecture and the infrastructure architecture together designed for it. And that's the thing I'll be going a little bit how the infrastructure from the data center with the modules within the data center and a critical sub-CDN evolved into a different aspects of it, right? So suddenly the data center that you have seen in the previous topic we talked about will become something like this, which is a cloud's logical structure, right? If you see here, I have a cloud, whether you take Amazon's or your own any public cloud for that matter, or Google, or I'm just taking the industry thing, but you can take any cloud. They typically get into this particular logical structure. They have to design this way for you to give at least close to something, get to 5 nines, 4 nines, 3 nines of availability and scalability. So this is how the clouds will look like if you look at it. So there's a cloud, which is a base URL that you go to or IP you go to. They typically go to the regions. The regions will tell you basically is completely independent of each other. That is, if you deploy application region 1, it is restricted to that particular region, but it's not shared anything with the region 2 and region 3. So regions are almost like a mini cloud under one cloud. So typically people deploy this to isolate completely data, everything, network and everything from each other. We'll go to this level when we talk about security impacts and all that, right? Then under regions, we'll have a zones. Zones are basically, you can say, like for example, if you take any cloud, either Amazon or Microsoft or anything, you'll have a zone in a India zone, a Singapore zone. Within India, you probably have a Bombay zone and maybe a Calcutta zone. So zones basically tells you, okay, within this zone, whatever is deployed will be available for everybody. And it's also called availability zone. That is, if the zone 1 fails, zone 2 still has available for you. That is, if I deploy application in both zone 1 and zone 2, the zone 1 fails, zone 2 is available, and you can. So the impact on zone 1 or a destruction, or say, for example, something is broken down or power went off or the floods came in and the zone 1 is gone, zone 2 will still be there. So when now you have a structure, now you can see that applications have now can deployed in zone 1 and zone 2, and suddenly you have availability is increased. So even though zone 1 is going down, zone 2 is still available and application is available, right? Similarly, under zone, you'll have a sites. Site is typically mapped to one data center. Sometimes it is more than one, sometimes less than one. It is all convenience of how the location is and first is maintained and all that, right? But typically site, they don't expose, the clouds don't get exposed more than the below site. They'll do up to site level. So every zone will have one or more sites, and every region will have one or more zones, and every cloud will have one or more regions. So now this gives you a redundancy in the entire infrastructure, and they are homogeneous. So whatever is available in zone 1 typically is available in zone 2. So the application has certain requirements of either compute or storage or network services. They'll all be available. So you can deploy both. Now suddenly now you talk about reliability and scalability, right? So since the infrastructure has evolved that, as an application programmer, as long as I can design that it can run in parallel, multiple instances and not conflict with each other, as an application provider, I don't have to worry about the reliability. I don't have to worry about the availability. It is taken care by the infrastructure. So that's how the infrastructure, the cloud structures have evolved to make it this possible to the application developer. So it's the end users, right? So now if you look at this, right, you'll have a cloud management center place. I will have one region or a zone in, say, South America, one in Middle East, one in India, one in, say, Australia, and they all managed at the same place. As an application developer, I just deploy it in all zones, the same application, run in the same from different places. So if something goes wrong, they all, other zones are available, and thereby you can easily achieve, if not 5 nines, but 3 nines and 2 nines or whatever, right? 2 nines is a pretty lame thing right now in the cloud space, but at least 3 nines and 4 nines, and you can have to know, right? So that's the that's a structure that looks like. Now, within the multiple zones, as I told you, you can have multiple zones within a data center. These are all convenience of how you build these things. Then you have availability zone, one or more hosts grouped into a cluster grouped into a pod, and a pod grouped into a zone, and zones will go into managed by the one management server. As again, I'm going to repeat here, it's that this is how the infrastructure has evolved to map to your application requirements of availability, scalability, and all that. And just remember this cluster pod zone, they have their own meaning to it, what they do it. But I will not go into detail of those the interest of time because I'm already reaching. Again, these are some of the clouds that I designed, some blueprints, where you have infrastructure, hypervisor storage, availability zones that are mapped to it. And if you actually physically go into blueprint, this is how your one zone or a data center will look like, so to say, right? And these are, this design used by the Cisco UCS, but it's independent of that, where you have a storage, where you have where you have network. And you can imagine, right? This is the cloud infrastructure the one has to build to make the application programmer not worry about certain aspects of reliability. And imagine if this is not there, you will have to write the code into it. Hey, is this system available? Okay, number of users are coming in, increasing. What do? I go and instantiate some other, and then that will have a latency and all that. So that the infrastructure will take away that complexity from the application programmer, so the application programmer can focus on what is important, which is the business logic of it. Okay, so I have 10 more minutes, but if I leave some for questions, I'll probably have 5 minutes. So I'll run through it. So next one is the performance. We talked about that another factor that impacts the applications. Application metrics, but how the infrastructure does. So you have a GPU-based process for doing heavy computing intensive applications. Then you have edge computing so that you have latency is less. So I can push the compute to the, almost to the IoT devices, if not IoT devices, but at least to the mobile applications, so mobile devices or the laptops or the browsers. And also, as we talked about CDN clouds, which will make they automatically manage depending upon the trend of the thing that they are seeing the request, they will manage the, the storage that pushed into this particular edge point so that the performance, that is, there's no latency. Like, for example, today, you ask for google.com, the page that I get is not served from the same place as you get or my colleague who is in US or in Europe. They all see the similar page, but they're all served from different places so that you get the latency. So in fact, the CDNs work with the telcos, and some of these telcos actually provide these POPs or pods, sometimes they call POPs. So this is also architecture that evolved to bring the performance. As an application provider who is serving google.com, I don't care where these things are. As a programmer, I don't know where these things are served to the users. All I care about is that how well the google.com looks like, what is the logo I put in there, and that's all I do, the content I deliver, and that content gets distributed. So the cloud infrastructure will take about all this distribution and give you the performance, which application programmer. At some point, they do worry about it, how much you put, how much you compute, how many APIs you call, and all that. But for most of the static things, they do that. They also do compression, and they also do a lot of other aspects that require security and all that at the edge level, almost, to give the performance. Okay. So next is a security consideration, which is another one, which is application requires, and the infrastructure provides, which is isolation. Isolation at a CPU level, storage level, or network level. At the CPU level, you have virtualization, you have a Docker that will provide you at a CPU level isolation, at the storage isolation level, then you have update storage that gets replicated into all the regions, so all the sites, so that you have availability. Network level, you want virtual LAN so that an application is working on one particular network, does not talk to the application on another network unless it is approved. This also becomes a scalability requirement. That is, if you put in a data center, the number of IP addresses that you can have will be restricted by how much of ports, how many number of ports you have, and what kind of switch you have. So you have to have a virtual networks to isolate between the applications, or it becomes very complicated. But virtual LANs have a limitation. Then you have a technology called GRE, which is basically one more layer on top of IP, TCP/IP, or other VLANs. That basically I can define whatever I want as far as the tunnel is concerned in the network, and that tunnel belongs to me. And I can just coexist in the same network, but it will be still virtualized and isolated to me. Then came into software-defined networks. Again, each topic is a pretty big one. I'll not go into each one. So isolation at a different level needs to be provided to the applications, so that applications are secured, and applications themselves don't have to worry about that. And the infrastructures have gone to that. So humongous research went into this, and and amazing products came out to provide this, so that as an application developer, I worry about just my logic, right? So that's the security consideration. The last, not least, is the burden of development. I'm going to take a few more extra minutes here, because this is another important aspect of it. That is, when I build an application, I don't worry about where it runs. Where it runs in the sense that, does it run on an Intel CPU or AMD CPU? Does it run on my Mumbai data center or a New Jersey data center or London data center? I don't worry about it. What kind of storage it has, I don't worry about it. What kind of network it has, is it a Cisco router or a Juniper router, or open source software. Literally, applications don't have to worry about those things. So that kind of a mobility has to be given to the application developer, and our application developers want that kind of a thing. So now that layer of layer of transparency has to be given it to the application provider by the infrastructure. So a lot of technologies went into it. There's a block storage, object storage, at the network level. How do I do virtual port? So what it means basically right now is that anything that is required by the application becomes application definition. So as an application, sorry, hello. Yeah.
Go ahead.
So that's the requirements that application. Now the application definition has infrastructure. So suddenly now application guy defines, hey, what my data center should look like so that I can run it anywhere. What are the minimum things? So what are the firewall rules are required? What are the load balancers required? So this requirement of, hey, I will define what I need as an infrastructure for my application to run, and then you run it anywhere you want, which basically means that infrastructure has become part of the development, a part of the code, right? So that has actually changed entire cloud infrastructure. So they all become services. So if you look into it, right, application logic. So now my data center template that you see here is actually code. If you see this, this is a visual representation of the definition that I need for this. This is obviously specific to one particular cloud, of AWS, Amazon's cloud, but every cloud will have their own definition of application specifying what is the infrastructure, what kind of CPUs required, how much amount of storage, or what kind of storage requires, what kind of network services. And now you can take the definition and deploy anywhere, any site, any region, the kind of cloud architecture that I talked about. And then the cloud have to execute that particular data center requirement, create a virtual data center for that application, run the application in that data center, and give back the services to the users, right? So if you look at the typical application stack, if you see, you have infrastructure on the bottom, you have OS, typically database service, you have business logic, then you have web server, UX, API, and security. Now, the entire application architecture impact or the infrastructure has changed to take care about everything else so that you can focus on things. So initially it was infrastructure virtualization, then OS virtualization, then you have web server virtualization that as a service, API management. Obviously API is still part of your application definition, but the management of API has been taken care of. That security has been provided by somebody. So all these layers have become service on their own. And right now, as an application developer, all I have to worry about is business logic. What do I do? For example, payment application. If I get a transaction from user one and I need to give it to the business logic, bank, how much do I put interest, or how much I do take my service charge? That's your logic. Or what do I tell? Whom do I tell? Or how much credit I have to give, or what kind of coupons I need to. That's your business logic, and you focus on that. Whereas where it is to be stored, how that storage needs to be maintained, where it is to be run, what the security I need to provide, and if the number of users are increasing for that particular service, how do I run more instances of it? Where do I put that in? All that part is taken away and put it in infrastructure, but that requirements are given by the application. So if you look at these things, entire definition of your application and infrastructure, whereas the services are becoming independent, pulling out the logic, separating the business logic and everything else, but the definition of it, what is required, has merged into application definition, right? So slightly confusing, but it's basically infrastructure is telling you, I'm just a service. You tell me what you want, I will execute everything else. All you care about is the business logic. So that's what enabled, the infrastructure to provide all the aspects of application except the business logic. Now, I'll cut short here and talk about where we are right now. Now, we have public clouds already there for last, 10 years or so, evolving rapidly. They're increasing the reach everywhere. They're increasing number of services that they provide. But they're also trying to do is a purpose-built infrastructure. So if we have a purpose, a very specific applications, and we need a specific hardware for that, you get that, like GPU-based clouds. Quantum computing. That's still in the infancy state, but IBM has that. Google just announced that. There's a lot of research going on to it. So if you have a very specific application, you can run there. Similarly, there is a lot more services. We talk about serverless computing, ALML services, template-driven programming to reduce the amount of programming you do, API management, which is basically a service management, who can access what, how much I need to, how do I throttle it, how do I secure it, and all that is taken away from the application, putting in the infrastructure. But what is required for the infrastructure is given by the definition of the, definition by the application itself, right? So that's the, I'm rushing here, but that's where the lot of research is going in and a lot of development is going on right now in this purpose-built infrastructure and availability of more services to make developers' job easier, right? So the takeaway is that, the infrastructure is changing rapidly to meet the demands of the application, which basically means that you have an application, you have to ask whether you are taking advantage of those infrastructure or not, or what else you require from that. So you literally have to revisit all algorithms and computing models that you have to see if are they taking advantage. For example, what we are doing on the current startup that I'm having, we are taking the existing database technologies like cube construction and saying that, hey, I have a serverless compute. That means that I can instantiate 30,000 computers at a given time for a split of second, for a few seconds, which means that if I take an algorithm, which I do in indexing algorithm in a sequential fashion, but if I parallelize this in a 30,000 way, I suddenly can compute the entire cube on a petabytes of data in a matter of a minute. And then the data center of the size of 30,000 machines come up and go away in a matter of a minute or less than a minute. Because the cloud enables me for that. Cloud enables us to do serverless computing in a split second. I can run a thing and do the function and come out and gone. So basically, I'm almost like setting up the entire machine, run one single function, come back, and the machine is gone. I'm not holding the machine at all, which basically means that I can use the infrastructure idle time to do a humongous computation. So right now, this much of parallel processing is not even done in the parallel processors we had in the 80s and 90s. That much of parallel. So now you have to think about, okay, how do I write my sorting algorithm? What does it mean to write a sorting algorithm on AWS right now, or Azure, or Google Cloud? Because it enables, it's just one API away. So suddenly your programs can run really, really fast and really, really efficient and really, really cheap. So that you need to think about every algorithm. So that's what in our current company we are doing. We are almost all the database technology algorithms we're rewriting to take care of and make use of this kind of infrastructure that we have. And we'll push the infrastructure to get to the next level as well, right? Similarly, application and infrastructure are merged. Now you have to think about infrastructure, what it requires, because you can define that within application and deploy it so that you don't have to worry about all the factors that we talked about, user growth, performance, scalability, and all those. That we need to think about it. And also developing, as a software developer, now it is more about integrating different services than writing everything on your own. So your curriculum and your education curriculum or your training or the way you build products will look slightly different because most of it is available as a service. All you have to worry about is the business logic. I'm talking about applications, right? Systems programming still remains same almost, but that's where it becomes right. So that's where I'm going to conclude. I know I am 5 minutes over, and I also apologize for the slides for next first 5-10 minutes that we ran into. So conclude and take your questions if you have any. So thank you.
Thank you, sir. Here we have a question. How the cloud deployment can be done through simulation?
Sorry, can you come again?
How cloud deployment can be done through simulation?
I'm trying to understand the question.
Okay, I'll just pass that question to your personal chat window so that you can read and answer.
Sure. Okay, I have one more question that I'm seeing in the chat window.
Yes,
when quantum computing becomes available commercially, how does it affect the cloud architecture? It's a good question in terms of what is happening in the current cloud. It is a hot topic, and those people who are interested in building cloud infrastructure and researchers and all that. Right now, the commercially available cloud computing is IBM's cloud. IBM has that. And again, I'm not from IBM. I'm not pitching any of these companies. I don't belong to any of these companies. But a bigger discovery has happened recently. Invention happened in Google aspect of it. It is not commercially available. The application that they are building, because the application itself will change dramatically to run on this cloud computing. When they will be commercially available, it depends upon how much demand they will have, and that depends upon how much applications have to take care, or rather demand applications have to change, right? Because suddenly applications will run 100 times faster than current mode because you have qubits rather than binary bits. They can have a number of states, and so which basically means that all the factors we talked about, scalability, user growth, they don't become a factor in terms of performance. They all become one. This just one, because any number of load, the quantum computing will not change. It will still remain same. So when it will be available, God only knows when that will be. If we're looking at least 2, 3 years, 4 years before that, right? Before it even become. But if you have something interesting problem to solve using quantum computing, it is available, but you have to go and request certain things from IBM, and they will give you slot, and you can use that. And they already given it to some universities and stuff like that, so I know that aspect of it. So, okay, I still don't understand how cloud deployment can be done through simulation. I mean, there are labs which help you to deploy clouds to see how we deploy it. But, this can be, I'm not sure how we can simulate such. What aspects of cloud are you going to simulate? Because there are lots of aspects of the cloud that, one is all the way from space. Okay, how much space am I taking? Second is how much energy I'm taking. How much, so you can simulate those aspects of it, but scalability and reliability, building a simulator for that, I don't have a good answer for that, sir. I'm sorry about that. I have another question, which is how can we save energy in cloud computing? Okay, so there's something called power and energy ratios that we talk about when we are building data centers, which basically is that how much power do I take to it? So there's a lot of research. Somebody should look at Open Computing Forum, which is predominantly funded by Facebook, and a lot of other people also joined, Intel and AMD and Microsoft and everybody there. They talk about what does it mean to save the energy. Now, in a very general fashion, you save a lot of energy because you're all putting all your computers in one place, which basically means that I can take advantage of central cooling, and also I can have a very innovative cooling. And if you look at some of the data center that we talked about in the Open Computing Forum, we have data centers under the sea. So which basically means that I don't have to spend too much energy in cooling, because the number one cost in the cloud is not the hardware, not the software, but actual power to cool. The cooling is the number one aspect of it, of the cloud computing cost. And we have done a lot of things to do that. We have taken in the data center underground. We have taken the data center to be a dark data center, so nobody enters. The cooling requirements are maintained well, because the heat that gets generated because of these computes are literally, have to be controlled so that these computes work fine, the devices work fine. So how can we say a lot of aspects of it? One is you decide where you're putting your data center. That determines one. That is, if you're putting in a hot places, obviously you'll have a lot more things. That is to just talk about the power that is required, which is the biggest cost of the cloud. The second is also about the latency, which is how much you need to work on the network aspect of it to provide enough bandwidth. Like for example, whoever has put in data centers, though it is not conducive for temperature-wise, but the network capacity-wise, it is very conducive to. So they all put in Mumbai. So Mumbai is one of the hot centers for people to put data centers and clouds, because they have undersea cable terminating almost at the India Gate. I could see that. I actually worked on first cloud data center in India, which is a Tata Communications data center. They had a pipe coming in from the sea directly into the building right next to the Taj Hotel there, right? So these are the things that are impact the energy costs. And so, again, it's a big topic. I'm sorry, I can't give you a very concise answer there, but there are different parameters you take while building these things. I have another question, which is regarding GPU-based cloud, how best we rely on getting compute, can rely on getting compute-intensive tasks. GPUs are the latest ones that guarantee a lot of compute power, but they're very specific jobs. Not all compute intensives are GPU conducive. Most of it is basically our graphic intensive. That is a lot of math and matrix based. Like you're manipulating a lot of matrices, and you're doing a lot of computation and in X and Y and Z fashion. The GPUs really help to build your tool. And almost all public clouds, big public clouds, actually give you GPU based thing. And now whether the GPUs may not be available in all the sites and zones, you need to be particular about that. When you are building it in the public cloud, you need to see whether that's available or not. Second thing is the GPUs themselves are evolving. One of the biggest vendor in the GPU is NVIDIA. They started focusing on only in the graphics intensive loads, but now they're almost going to the level where they're providing GPUs for AL and ML workloads as well. And they are even talking about the chips, that some of these algorithms can be put in the chips itself and make them as available. And these cloud providers will pick it up, make one of the parts that we talked about, one of the logical structure of the cloud, be part of that so that applications can be deployed on that when you ask for the GPU, and then you do it. And can we rely on that? We have no other choice. The GPUs are actually built well, and I know I had customers in one of the companies where they used that and got a very good results. But I'm not an expert in GPUs. I'm an expert in whether they gave the reliability or not, and I have pretty positive results in that. How does NVM-based memory affect the data center performance? The data center performance, I mean, it is cloud doesn't, or our data centers don't actually impact algorithm. Like, if you have NVM based memories, I'm not an expert in the memory chips, so to say, how much power they consume and all that aspect of it. But, short answer is that depending upon the characteristics of that memory, the power requirements, you shouldn't have any other adverse effects of it. I know I'm not giving you a good answer there, but that's the knowledge that I can go to level in the memory aspect of it. Okay. Okay. I think that probably explains the question behind the question. So the question says, can we make data centers stateless because NVMs can help when the system restarts and up, so we can save energy? Okay. That aspect of it, it's not about the data center itself. It is about how the operating systems maintain the state. Obviously, it's mostly about the hardware that, if you look at the structure of the cloud infrastructure, they don't assume anything about the hardware specificity, except the logical. Like, for example, if it is network, hey, how much logical networks can you give me? Virtual networks give me? So it's about the individual CPU or brand of device that I use that let you. Obviously, if I'm rebooting continuously, or I need to reboot continuously, or I have to move one particular workload because I'm taking away the pod or a section of the pod, so that all the applications can move from one to other pod without having to interrupt or letting to know the admin. In that case, the performance, the stateless parts of these things do matter. But in the cloud infrastructure, they don't rely too much on the hardware part of it. They rely at a software layer part of it. Like, for example, all the hypervisors, they virtualize the memory, right? Obviously, the performance of NVM stateless things does help the virtualization memory, but how well your virtual memory, which is in your primary storage, can be moved from one pod to other pod. So do I put the storage common across all the things? So this is where actually a lot of this hyper-converged infrastructures also come into picture. So those aspects will matter to the performance of the data center, or data center remaining to zone into the cloud, right? Building into the cloud. So they do matter, and any small percentage improvement will largely improve that, because in the end, availability, performance, RSS, stability, reliability, all that is bottlenecked by the state, because if the application has to have a state and that has to carry across, you will have a problem, because that's what becomes. The moment you become stateless, for example, in the serverless architecture, they expect you to be stateless. Then you can scale randomly anywhere, you can kill anything, come back anything, you don't lose any application logic or application performance. So that way, for a virtual memory management of the hypervisor, the stateless will make it really less load in moving the workloads from one pod to other pod, or one data center to the other data center. So it does actually impact, if that's what you're asking about. It will, at the moment the virtualization layer has to work less, it will require less power, and that way it will require less energy. So yes, you're right, and those things will matter to the cloud. Now, another thing is, can we rely on cloud for real-time operations? So real-time is a pretty overloaded term. So when we talk about real-time, there are two aspects of it: real-time in a user perspective, or real-time in a system perspective. So none of them guarantee real-time. None of the clouds will guarantee real-time. They'll guarantee the availability. That is 99.99 or 4 nines or 5 nines or 3 nines, they are well. The reliability wise, or the real-time wise, they don't guarantee because there are aspects that are there, which not in even the control of the cloud. For example, you connect to the cloud, there's an ISP of yours coming into picture for the performance. So, for example, you build a data center in Mumbai, the way you connect through is through Airtel or through Jio or one network, and the latency of that is determined by them, not the data center. Right? So they can't guarantee you the last mile or last 2 layers of the connectivity for you. So that one. The second one is that most of the clouds are built on virtualization, which basically means that there's one more layer on top of your CPU and memory, which basically takes you far from the real time. In a traditional fashion, when you say real-time operating system, they guarantee you certain time slots. That is, if this operation takes a fraction of a second, I guarantee you that it will always take a fraction of a second, which basically means that you need to have an aspect of, oh, I need to pin my process to a CPU, or I have to pin my process to a particular memory segment. And those are the guarantees that operating system has to give you, which hypervisors don't give you. Now, can we build a cloud which will guarantee you that? You can certainly build that. You can do a bare metal cloud, put a real-time operating system like, I know, many of them out there in the world, and provide you these aspects of pinning memory, pinning CPU, so that you always have a guaranteed response from the underlying infrastructure to do that. But if you consider the round trip to the end user, which is a consumer of your service, then you're suddenly out of the place, because that is a aspect of the network that you never guarantee. So, but if you look at generic cloud, 99.99%, they will not guarantee you any real-time operations. Having said that, you could have pretty good response given all these things in a type of applications that we are used to. For example, today you open Google or Bing or whatever favorite search thing you type in, before you could type in, it actually tells you what you want to search for. Imagine the amount of computation that happens to you to give back the results before you even think about it. So that way there is a real time, but that's certainly user level. There's no guarantee. Sometimes it may come in a second, sometimes it come in half a second. So when typically in a theoretical fashion, if you say real time, it's a guarantee of the delivery that none of the clouds today give you. Okay. I'm beyond 20 minutes of my scheduled time. So I'm happy to take any questions if you have. You guys have my email ID. Reach out to me if you have any questions on that. I hope it is informative and useful to you and worthwhile your Saturday evening time, which you spent away from your family. I hope it is worthwhile for you guys.
Thank you very much, sir,
Thank
for
you.
the useful information about application architecture and impact on infrastructure. Thank you once again. I
Thank you.
sincerely thank all the participants for their patience as well as cooperation. Thank you very much.
Thank you. Bye.